All right. Welcome everyone to our last speaker event of the quarter. We're super honored to have Professor Lerch from Georgia Tech to come in and speak to us today. It's I'm super excited. I've read some of his work and it's really cool, really fascinating, and I can't wait for you guys to hear more. And I'm super excited to learn some too. So without further ado, let's get into it. Professor Lerch, if you want to take it away.
All right. Thank you very much for the introduction. So let me start sharing my screen. Oh, can you enable screen sharing for me, please?
Sure.
So what I'm going to talk about is basically a little bit all over the place in some ways. So I want to give you a very broad overview over music information retrieval, which is the field I'm working in, where we talk about basically machine learning and music in general. And then I want to go a little bit deeper into some issues, some typical issues, and how my work tries to address these issues with two examples. So generally, this is, I'm fine if this is relatively informal. We are not too many people, so please don't hesitate to speak up, interrupt as well. That's all fine. So for the QR code there, so all the slides are on GitHub. If you're interested, you can just scan this QR code or go to Alexander Lerch at GitHub, and then you can see these slides. All right. So I wanted to start giving a very brief overview of myself. So I have a electrical engineering education. I also majored in as a Tonmeister in Germany. That's a classical music production degree at the University of Arts. And after I graduated, I actually co-founded a company called Zipline Development in Berlin, where we did music processing solutions, basically that we licensed as technology to other audio software companies. So, for example, if you're familiar with software like Ableton Live or Steinberg Cubase or Avid Pro Tools and so on, then things like the time stretching and pitch shifting engine in there would be from our company. And then after a little bit more than a decade at my company, I decided to do something else. And since 2013, I'm a professor at the School of Music at the Georgia Institute of Technology. Right. So generally speaking, I have a lot of audio algorithm design experience. I worked on commercial music software for more than 10 years, obviously in a startup environment. But then gradually my interest shifted more from signal processing towards applied machine learning, which is mostly what I will be talking about today. In order to introduce the field and the impact of machine learning on the field, I want to kind of systematically put this into context a bit. So when we talk about music, there is actually a chain of musical communication that we can establish that goes basically from the composer to the listener. And I want to quickly go through these individual stages here. So it starts with a composition. Composition does not necessarily have to be written down as a score. It can be in your head, but it defines a style, idea, a structure, etc. that makes kind of the core of the music. But then the music doesn't exist yet without being performed. So the performer kind of takes the music and renders it into an acoustical rendition of these ideas. And by doing that, it will be interpreted, it will be modified in some way. There might be information added or dismissed from the original composer's idea. And while this whole concept is a little bit focused on like the chain is established for classical music, it still fits to some degree for many forms of music, right? So this is not only for classical music. Then the performer, at least when we talk about analyzing music or processing music and so on, this music has to be recorded, has to be somehow available in digital form. So there's usually a sound engineer involved. They will change timbre, they might edit and splice the recorded signals and put them back together. They might apply effects, etc., etc. Practically for the analysis, we cannot separate the performance and production stage because it's one recording that we are dealing with. And then we have the last two stages where it's actually about distribution. So when we talk about streaming services, that would be a typical distribution. And then we have apps or we have devices where we listen to music. And so on the next slide, I have the same chain of musical communication, but now I will give some examples of how machine learning will actually or already does impact these various stages of musical communication. So when we talk about the composition, as you all know, generative AI is the big hype at the moment. So obviously, it's only a question of time where we will have really musically intelligent, at least co-creational tools that allow composers to get ideas for arrangements, etc. There are already quite a few systems out there. There are startups doing this. Here's an early example that's not from my group that just harmonizes a Bach chorale in the style of Johann Sebastian Bach. Let me quickly play a few bars. Wait, I didn't share the audio. Wait a second. I need to... How do I change this afterwards? Share sound. Okay, let's try that again. So this is actually not that exciting. It's actually already a couple of years old, but it gives an idea of how you can actually achieve something very realistic, especially when there are constraints with respect to voice leading and so on. But obviously, current systems already go way beyond the capabilities of such a system. And there is actually a clear expectation that in 1 or 2 years, we will have potentially very good automatically composed music. And if you listen to the marketing, then you already have it. Second stage is performance. So obviously we will have, so music education is a big market, and intelligent music tutoring tools that listen to you play and then give like concrete feedback about the details that you did well and did you not do so well, etc. This is definitely coming and partly already there. And there will also be some kind of generation of human performance. And what's interesting about this is the various forms this can have. So, for example, a colleague of mine at Georgia Tech works on robotic musicianship. So he builds basically robots which play or who play musical instruments and try to interact with humans on stage. But there's also the possibility of having a complete virtual artist generating this. And again, a very old example that just shows the concept is Hatsune Miku. That is not really existing Japanese pop star, which is actually not AI generated or anything. This is really curated by humans and produced by humans, but it shows the potential of actually having a complete artificially intelligent artist. And I find, again, this is a couple of years old, but I find it really fascinating that even at that time, a non-existing artist would be able to fill actually huge concert spaces with a real audience. So I find that quite an interesting example. I don't have actually more audio samples, which is maybe a little bit disappointing, but generally going through this in the music production world, obviously the AI tools or machine learning tools are already partly used by, for example, creating auto mixes or adjusting effect parameters depending on the content, adaptively, automatically editing and cropping audio files, etc. And that will also become more and more. You already daily interact with recommender systems in some way. So music recommendation is actually mostly not driven by the audio content, but partly it is. And my guess again would be that in the near future it becomes more and more so. And there are other ways where intelligent music discovery tools that are context dependent, user dependent, and so on will become more prominent in the near future. On the listening side, there is again discovery, but I think there's also a huge potential here about interactive listening tools where the user can actually say, I like this song, but I want to hear that song with different instruments. And then that is automatically converted or generated. Or I want to replace the singer with Taylor Swift or something like this. And having this adaptable music, I think is an interesting concept. In order to achieve all these things, we need to make our computer to understand musical concepts, right? So we need to be able to train a system so that it actually either generates musically meaningful things or categorizes it into musically meaningful categories, etc., etc. So for all of these tasks, the first step is to train a computer to understand music. Now, if we do this very traditionally, that would look like this. So we have an audio signal coming in that's basically just a series of amplitude values. And then we would split this into little blocks and extract so-called features or descriptors from it. So for the features, they should be relatively compact, so it should be much less data than the audio signal itself, but they should also be relevant, obviously, and then easy to analyze in some way. So a feature of an audio signal, it might be something as easily understandable as a fundamental frequency as it changes over time, but it might also be more unintuitive ways of describing the spectral shape of a signal or the timbre of a signal in some way. And then we feed these features into some kind of inference engine that might be a classifier, that might be a regression algorithm, or that might be some rule-based system even. And then we get either a categorization or something else out of it. If we stick to this classifier example, nowadays a standard baseline system for audio classification, for example, is not as easily split into two parts like feature extraction and inference, but it's more a monolithic system. We still use the word features. You see here in this plot, for example, we have feature maps here in the middle. But ultimately, the idea is that you feed in some kind of, usually a spectrogram-like representation of the audio signal. Then you have a convolutional architecture that kind of condenses the content over layers. And then you get this feature map that is then the input to a relatively simple classifier or classifier head at the end. So what we have here is definitely much less required expert knowledge, because we don't need to design those features that are being extracted, but these features are just learned from the data. So that means we don't need to tweak this too much, but we actually have to take more care of the training data and the general experimental setup and so on. But most importantly, we require much more data to be able to properly train this. So we have a lot higher data requirements. And this is actually kind of the topic that I want to spend on for the rest of the talk. But first, I want to give you more specifically a quick overview of the general tasks and my areas of interest in this field. So when I talk about audio classification, there are plenty of things you could classify within audio. So there's, for example, musical style classification. You might want to detect the instruments that are there. You might want to create tagging labels as you have them on streaming platforms. You might want to detect the mood or the artist of a piece of music, etc., etc. Then we have the field of music transcription, where we have an audio file, and then we want to extract, hey, what is the main melody? What is the pitch sequence of that? What is the chord sequence? What is the chord progression in this music? What is the structure? Where are the choruses? Where are the verses, etc.? What is the tempo? What is the musical key, etc.? So there are plenty of things that we might want to transcribe from the audio signal. We might also want to process it. It might be a mix of a pop song, and we might want to say, hey, this is all cool, but I want to extract the drums from it, or I want to suppress the drums from it so I could put in a different drum track. So this would be a source separation task where we try to, from this mix of audio signals, try to then extract the individual sources again and separate that from the mix. And then last but not least, this generative AI part. I have worked a little bit on controllability here, namely how do we actually control individual parameters of the generation. So many generative systems, if you look at them, are actually kind of, they generate something on a button press, and then either you like it or not. But what we worked on was more, how can we actually give the user some control here? So something is being generated, and generally it's okay, but we want to make it a little bit more rhythmically complex, for example. And then we try to find ways to actually include that control in generative systems. From a technical point of view, I approach these tasks that are introduced from like I try to solve these with different focus areas. So one is definitely representation learning, where we can try to learn a representation that is more generalizable, possibly for music, and then apply it to different tasks. Secondly, machine learning with insufficient data is actually what I want to focus on today. And then I also have another area of interest, which is actually about the evaluation of generative systems, because it's actually scientifically kind of meaningless if you create a great generative system, but there are no ways of actually measuring how good it is. But again, as I said, I want to focus on this machine learning with insufficient data. So that means I will first talk a little bit about data and why this is actually a problem. And then I will introduce two approaches. So then we will dive a little bit deeper. I hope you bear with me there into machine learning. One approach is called reprogramming, where we utilize a big pre-trained model and try to do some pre-processing to improve classification. And one approach we called embeddings as teachers, where we use, like, again, a pre-trained model, but not directly, but only the embeddings during training, and try to train a smaller model with improved classification characteristics. All right, so let's talk about data. Obviously, when we talk about machine learning, it's just a generic algorithm that maps an input to an output. But instead of the engineer creating rules how to map this, or creating this transform how to map this input to an output, this mapping function is actually learned from the data itself, from specific patterns and characteristics in the data. And that means that a model success largely depends on the training data. So if we have a bad set of data, and bad can mean multiple things, then it is likely that our machine learning algorithm will actually not learn the right things, and we will have suboptimal performance. So the general challenges that we deal with when we are looking at data is that, especially in music, if you have users assigning labels, for example, tags to music, then these might be very subjective, right? They might there might be labels like "this is intense" or whatever. I mean, who knows what that actually means, right? It means something for the user and listener, but not necessarily for everybody. So there might be disagreement between users about, for example, genre categories, right? So there will be some noise in the data as well. Imbalance and bias. We have some musical genres which are much more ubiquitous than others, and that therefore these genres will be potentially overrepresented in our data set, and that might actually bias our classifier or general machine learning algorithm in that direction. Similarly, we might not include all possible genres in our data set, and therefore it's not representative, and so on. But again, and I said this multiple times now, I want to focus on the size of the data sets first. So music data is not scarce. You know that music is easily accessible. There might be some copyright and licensing issues in general, but still, I can go ahead and get a lot of music data to train with, so to speak. However, when we train a machine learning system, it's not only about the raw data, but it's also about the annotations. And consumer annotations are actually relatively easy still to collect. So we can parse, for example, YouTube comments. We can look at all music annotations. There are some other websites that collect these user data for music. So it's possible to parse it and download. However, if I want to, for example, build a transcription system, then I need detailed musical annotations, and these are really hard to come by. So just imagine, for example, that you want to train a system to detect drum hits accurately. So where does the bass drum and the snare drum play in a piece of music? To have a ground truth data, to have a data set that you can actually train with, there has to be somebody sitting down marking each drum event with a very accurate timing, like let's say plus minus 10 milliseconds. And that is very time consuming and tedious, and nobody wants to do it. But the people who could do it are also experts, because you cannot just give it to some high school student to annotate. So that means it's very time consuming, tedious, and we need experts. So that means that everything we have in that regard is these are very small data sets. And unfortunately, small data sets are becoming less and less useful, because as the modern machine learning systems grow more powerful, they also grow more complex. And the more complex they are, the more data we need for training. So we have, obviously, there's plenty of previous work on dealing with insufficient data. So we could actually, in audio, we could say, let's synthesize something. We have MIDI signals, and we can use a synthesizer to play these files. Obviously, there's a caveat here that it might not be completely realistic in the audio, but it might still work in training a system. We can augment our data. So in the audio domain, this could be, for example, time stretching and pitch shifting, changing pitch and tempo independently of each other. That might be remixing the audio with different files, that might be taking chunks of the audio. There are many ways of how we can increase our number of training samples potentially. We can use transfer learning. That means we take a task where we have a lot of annotations, and then we can train a really deep network with a lot of parameters, because we have sufficient data for that. And then we can take these embeddings without the classifier head and try to apply that to a new task with potentially a little bit of fine-tuning as well. So these actually have been particularly successful for many of these tasks. So transfer learning is really a good way to deal with insufficient data. And then we can try to utilize semi and self-supervised approaches where we take advantage of all of this music data that is easily available without labels, and try to build models with that in some way, and then use only the small data set with labels to actually fine-tune our model. As I said, I wanted to introduce like two very new. I mean, still, the field is moving fast, so maybe they are not that new anymore. But I think they are still interesting concepts. Two new ways of dealing with very small data sets. The first way is referred to as reprogramming. So when we look at this task, we observe that we have pre-trained models which can be very, very deep, and they are very powerful solving their specific tasks. However, they actually learn a lot more than just what is needed for a specific task. And then, similar to the idea of transfer learning, we can utilize these deep models that are pre-trained. However, here for reprogramming, the idea is we want to reuse that, but we want to keep the number of training parameters minimal. So that means I cannot just fine-tune the existing big deep network, but I want to find a different way to do this, and I want to actually keep the pre-trained model unmodified and only add on to this. So, and here is what reprogramming then tries to do. So in red, we see this pre-trained model here, and we actually deal with these pre-trained models kind of as a black box. So we don't change them, we just have an input and an output. And this pre-trained model is maybe trained for, let's say, audio event detection. And when we want to utilize this model, what we do is we add actually a pre-processing step, which is the actual reprogramming. It's so we transform the input into a input that works well for this audio event detection, and then we have these output classes, and we map them to our target classes. Our target classes might be, let's say, an instrument classification. So instead of detecting a dog barking, we map these output classes so that we have different instrument classes. Again, the pre-trained model is unchanged. What you will, if you're familiar with the literature, you will see that this is actually inspired by adversarial attacks, where we modify the input of an existing system a little bit to actually force it to output a completely false result. So here we want to do this in a non-adversarial way, but we want to process the input so that it's more suitable to solve a different task. So the experimental setup, very quickly, we use as a model that we work with, audio spectrogram transformer. So this has generally is a system that has very good baseline performance on audio event classification, and we use this actually on musical instrument classification. It's a data set where we have a lot of 10-second audio snippets, and they are labeled by humans. We do this by adding this pre-processing in front of this spectrogram transformer, basically the input. And that means we have a CNN, and then we also try a UNet, which is basically a typical structure that is used for source separation and similar tasks. And then we map the outputs as well. So in order to test this properly, we test only the CNN architecture, only the unit architecture for classification, and then we test the chain of CNN plus audio spectrogram transformer and unit plus audio spectrogram transformer. These are basically the four systems that we compare. So what we see here is that if we just take this audio spectrogram transformer pre-trained as is on the audio event detection, then we get a classification rate of like F1 of 62%, which is, well, certainly better than chance, since we have like 20 classes for instruments, but it's also not very impressive. And we get results in a similar range if we just use our convolutional neural network or unit architecture. So we always get around 60%, 60-ish. And what we see is when we actually use this CNN plus the audio spectrogram transformer, so we actually change the input, but leave the spectrogram transformer unchanged, then suddenly we get much higher classification rates with 78%, and then up to 81, 82%. And note that these are very few training parameters. So this is not the whole transformer that we retrain here. That's really just a tiny input transform that we train here. And we are definitely able to achieve state-of-the-art results by just doing that, by doing nothing else. So this has the advantage that we can train much faster because we only have these few training at a fraction of the training parameters there. but we are able to achieve state-of-the-art results doing that. So that, given that we have only this very shallow architecture for processing, that allows us to work with much smaller data sets, because we are not that much, we don't risk so much the effect of overfitting. The second approach that I wanted to talk about is embeddings as teachers. So here the question is more, I do have a small, relatively lightweight model, but I want to make it perform better by infusing extra knowledge, or by transferring extra knowledge from pre-trained models. And I want to try to do so without additional data labels or anything, just having the small data set that we have. So the idea here is to use like pre-trained embeddings that we can extract from very deep models that are around there. So maybe you have heard of some models like VGG-ish or OpenL3. So these are trained on large amounts of data and provide this internal representation that we can use as features. And then the goals are to at this very low complexity level of our model, impart that knowledge of these pre-trained models, and thus improve model generalization by doing that, and improve the classification rate here. And the way we do this is we take ideas from transfer learning, and we combine those with knowledge distillation ideas. So knowledge distillation means we want to distill the knowledge of a large teacher network into a smaller student architecture by actually training the student architecture with the behavior or the output of the teacher system. So what we do here is the following. We have the standard block, that is the blue block here, that would be our normal CNN classification chain, really, where we have our normal loss function, etc. But then what we add is this gray block, which is a pre-trained system where we take the embedding and we actually add a special loss that makes our student embedding in the blue branch more closely related to the embeddings that we have in the gray model from the teacher. And we add this loss simply to our training loss function and see what happens, essentially. So experimental setup here. Here we take a different task. It's not music instrument classification, but it's actually music auto tagging. So what we have is 50 most common music tags that we want to assign in a multi-label classification task, and our input audio consists of 30-second snippets. And then again, we have a baseline system, which is just a simple student CNN architecture that we train. Then we have these embeddings here, different teachers. I already mentioned VGG and OpenL3. They are PAST and PAN. These are different embeddings trained on different data with different architectures, but generally these are just pre-trained systems with trained on large amount of audio data. And then we have a standard knowledge distillation approach where we train our students with these teacher soft targets. And then finally, we have our embeddings as teachers approach here, where we regularize the latent space with the teacher embeddings. And this is how it looks if we look at these results. So you see this is grouped by the embeddings, the pre-trained embeddings, VGH, OpenL3, PAST, and PAN. And then the different colors show the different systems. So we have our standard baseline in black. This is basically the student model that was not trained with any kind of teacher. So that performs here with a mean average precision of I don't know, 44%. And then in dark gray, we see the teacher model. So if we just take this pre-trained embedding and apply a classifier, just a logistic regression on it, then we get here for the VGG and OpenL3 features, we get actually relatively bad performance from it. But actually for these two features on the right, past and pan, we get a very, very high performance, which indicates that these pre-trained features are actually quite powerful and contain a lot of information. Then we see generally the knowledge distillation approach performs improves performance a little bit compared to the baseline. And then if we apply this additional regularization loss that we talk about, we see, especially for these less powerful features here, we can actually significantly improve classification. And for the very powerful features, at least we are significantly better than the baseline and then the knowledge distillation approach. All right. So ultimately, this concludes my presentation here. I hope that was a good balance between in-depth and overview. I'm not sure. So I presented two recent approaches to deal with the problem of insufficient data in music information retrieval. One was reprogramming, the other was, I call it a self-supervised regularization loss. And they both lead to models that are relatively compact in the sense of parameters, but still perform at or above even the state of the art in some cases. With different trade-offs, some have higher training complexity, some have higher inference complexity, like reprogramming, and so on. I would argue, so I think this is like a direction that I will continue working on, because this is really a fundamental issue in music, that we don't have enough data. But I'm also thinking about whether this is actually a more fundamental problem, where we actually have to address some flaws in the data collection and task definition process, and working on approaches with working with low amounts of data is maybe just covering up the problems a little bit. But this is actually a whole different talk, so maybe I won't go further into it. If you want to look me up, you are welcome to send me an email. You can connect to me on LinkedIn if you want to. If you're interested in this general topic of analyzing musical audio, you can check out my book, and there are a lot of resources also online as open source. And if you're interested in Georgia Tech music technology, check out my lab. That's available here under this link, musicinformatics.gatech.edu. All right, so I hope that, again, I didn't get much feedback here, so I hope this was an interesting presentation to you. I'm very happy to answer any kind of questions you might have. Maybe I stop sharing for now.
Yeah. All right. If you guys have any questions, you can put them in the chat, or just unmute yourself and go for it. Yeah, no, I thought, in the meantime, I thought this was super, super interesting, especially I'm getting into audio a little bit more and trying to understand the intricacies of, I really, the more I'm working with audio, the more I'm understanding the data problem that is faced. It's a really interesting topic, and I'd love to hear a talk from you about that too. That's just me, but yeah, does anyone else here have any questions? Cool. Okay, then what we'll do is I will stop the recording.